Let's see what comes out of this fancy hybrid stuff. Okay, let's get started. Hopefully things will work out. So welcome everybody. My name is Sławomir Nowaczyk. I will give this first lecture in applied data mining course. So let me start by telling a little bit about what the course is actually about. So what you are kind of expected here. So it's an introductory data analytics course. So it will tell you a little bit about what kind of data analytics you can do, what are the methods, and so on. So we will start by kind of explaining what is data mining, machine learning. Is this door locked? But this lady can still get it. So what is what people mean when they use those fancy buzzwords? In particular, what kind of tools you can use and what kind of problems you would want to solve with those techniques. So we will go through a couple kind of typical classes of challenges and so on. We will talk specifically about how computers can represent knowledge and reason about this knowledge, which is the kind of underlying theme in AI machine learning data mining. It's all about knowledge and discovery of new knowledge. So we will cover the symbolic and non-symbolic knowledge. We will cover certainty, and we will talk about some uncertain reasoning. We will talk about supervised and unsupervised machine learning. And basically the goal of the course is for you to be able to answer two questions. The goal is not to make you experts in AI or machine learning. That is not really the point. The point is for you to be able to use AI machine learning data mining when it makes sense. So in order to do it, you should understand when to trust machine learning data mining results. Right? If you are working somewhere and somebody comes and tries to sell you a new fancy tool, you need to know if the results from that tool are reliable or not. And you also need to understand what's possible with machine learning data mining. So when you are facing a problem, you should know, okay, is this something that could possibly be solved with data mining or not? Does it make sense to look for somebody who can help using those kinds of techniques? So there is a number of people who will be involved in the course. That's a younger version of me. And there is a couple more who will be delivering lectures, labs, project, and so on. So Reza, Mahmoud, Amira, Hadi, Zahra, you will all meet them in the course. We have two books listed as course literature. We will not be following them very closely, so you don't absolutely need to buy them. There is a lot of material online about data mining, machine learning. So you will never run out of stuff to read, even if you don't buy those books. The books are nice because they have nice structure, clear. You can kind of read from the beginning to the end. If you go to internet, Google, whatever, there will be a lot of good stuff and a lot of bad stuff, and it will be harder for you to figure out which sources to trust, which to not. But it's perfectly possible to pass the course without ever looking at any of those books. The course structure is pretty simple. I mean, you know that it's a 7.5 credits course, which means it's 10 weeks of work half time. They're supposed to be taking two courses in parallel. And if you do some math, it turns out it corresponds to roughly 200 hours of total work. So that will be divided into lectures. We will have 10 lectures each 2 hours. There will be some labs. So there will be 6 labs total. The idea is that the labs should take you somewhere between 2 to 4 hours. There's 2-hour slots when you will be working with help from Zahra. She will be supervising that. But if you are not ready with the lab during that time, you can catch up later. We will also have a group project where you will actually apply the knowledge you have gotten in some simple tasks to try to see how those techniques work in practice. So it's in the second half of the course. You will have a task, some data analysis to do, and then you will write a report, do a presentation showing what kind of interesting things you have found. And then there is the written exam. So for those of you on campus, we will have the written exam, the normal rules. For those of you who are not here, we will have an alternative oral exam, which you can do online. So up to you. You are of course more than welcome to come to Amsterdam for the written exam anyway, but we will have an opportunity of oral exam for those who cannot be here. And just to kind of give you a perspective of how this course is organized, any guesses what this pie chart could mean? It's called time management, so probably talks about time. It says hours, 200 hours, that's a number I have already mentioned. This is basically how the course is organized. So if you look at the times when we meet, or not just meet with me, but with any teachers, it's less than a quarter of a time where you will be in classrooms with us. Right? So a lot of this course is self-study, working on your own, based on the things we discuss. So all the lectures will have this, we will present the ideas, but the expectation is that you kind of go on your own and you deepen this knowledge. We will not explain everything during those times. There's just not enough time in the lectures. So you should do your own studies beyond this quarter of the time that is here. And not just 1 or 2 days, one door is open, but both. Thank you. Course plan. So basically the topics we will cover in the course. This roughly corresponds to the lectures we will have. So today I'm starting with the introduction, and then we will cover data preprocessing, we'll cover visualization, we will cover the big data platforms. Then we will start talking specifically about machine learning, supervised machine learning with decision trees, support vector machines, and artificial neural networks, some of the most popular techniques. We will talk about Bayesian networks, so a little bit more probabilistic reasoning. And then we will talk about unsupervised machine learning, mainly clustering and anomaly detection. So to cover kind of the breadth of the most important techniques in AI. And to some of those lectures, there will be labs. We cannot kind of cover all the things in practice with the labs. So we have done a selection of the topics which will be covered in the labs. And for the course materials, there are the books, but all the materials will be available in Blackboard. So all the lecture slides will be there, all the lab descriptions. So the Blackboard is the main place for communication. But if you need to contact us, I've listed myself here. So I actually mixed the room numbers, so don't trust the room numbers too much. I will try to fix that. But the emails are correct. They correspond to the right person. That's easy to verify. So if you have anything about the course as a whole, you can always let me know. And then Reza will be responsible for the project work, and Zahra will be responsible for the labs. So those are probably the 2 people that you will be communicating with the most. So that's why they have their emails there. One more important thing to cover is student presentations. So next week, the lecture will be you talking, not us talking. Actually, there will be a lecture when Reza will be talking as well, but there will be one where you will be talking. So the idea is that you will read a paper. You've already seen it on the blackboard. You can pick the paper to read. And then you will present in a group the main idea or contribution of this paper. So you will not have much time, just 10 minutes. So you will not be able to go into all the details. But basically what we want to have is we want to have a discussion about how those ideas from the research papers can fit into forensics, security, the related fields, right? So in a sense, what we want to start the course with is a little bit of motivation, how those techniques can be used in your future work. Because in reality, in the lectures and the labs, we will mostly cover quite simple techniques, right? We need to start there. So it will not always be entirely obvious how this is useful for the real world problems. So we hope that those research papers will give you a perspective of how machine learning is useful, and then it will be easier for you to see how those simple techniques can be kind of extended and made more realistic, and then they become useful. So that will be next week. So I've seen that most of you have already picked papers, but if you haven't, you should look at the blackboard and do that. And then the final thing about the kind of more administrative part is about course evaluations. So after every course, we have the surveys sent to you to get some evaluations. I don't know if you have ever seen those surveys. They are sent after every course, but sometimes I feel like majority of students just never see them because we have very low response rates, right? And we really would like to get your feedback in order to be able to improve the courses. We do want to make the courses as good as possible. So the surveys after the course is one part of that. The other part of the improvements is we have this idea for course ambassadors. Hopefully you have seen that before. The idea is that we would like 2, maybe 3 students who can act as some kind of interface between teachers and the rest of the group. It's always easier to talk that way, and basically to just help us get this kind of feedback, not just at the end, but also throughout the course. Right? Because at the end, it's a little bit too late to really change anything. But if we get your feedback early enough, we definitely can update things. So if any of you would like to be this course ambassadors, it's not a lot of work. Like, it's just talking to us 2-3 times throughout the course. Could be after a lecture, 10-15 minutes, just letting us know what you think about the course and so on. So just let me know during the break. And please, it is important for us. We would like to get this feedback. So, any questions about the administrative part, the organization of the course?
I see that you haven't uploaded the slides yet on Blackboard. Yeah,
I will do it just after the lecture.
Yeah. As for the labs, are there like submissions, stuff like that?
Yes, that will also be on Blackboard.
Okay.
Yeah, but the labs start not next week, but the week after. So until next week, you will be working on the paper. So the labs will show up afterwards.
Okay.
But it's everything will be on Blackboard.
Hi, this is a question from the online audience here.
Sure, go ahead.
Okay, thank you. So what if it's not possible for me to attend the seminar next Thursday, for example, or most actually, if any of the labs on the exact times? Is it possible to follow this course even though you are actually working, and would be prepared to put down the time, but on evenings and off hours?
So if you cannot attend the seminar, then yes, please send me an email and we can do an additional time. So something could be in the evening or something that works for you. That's not a big deal. We can definitely do that. For the labs, I guess I don't think we can have like an extra evening session of the labs, and those which are scheduled are already scheduled. I guess part of the question is, will you be able to manage without going to the labs or not? Right? Basically, if you can just complete the lab without showing up at the lab, that's not a problem. That's perfectly fine. And if it turns out that you need some support and you cannot get it during the normal hours, I think the easiest way is if you let Zahra know, and then you can try to arrange something specific. It might be like an extra shorter time where you can get some feedback, get your questions answered, or maybe it can be some kind of support over email. It will be easiest if you just agree on something that works.
That makes sense. And also just with, let's say, 1 week's notice, it's difficult to plan for what's happening in 3 or 4 weeks. Maybe, they can rearrange work schedule based on that. But I'll send you an email. Thank you.
So the schedule for the course is available, right? You have all the activities are planned. I guess you all have access to the university schedule, so you should be able to see when things are planned. Okay, any more questions?
I have a question, like how big groups can we be for the project?
For projects, it should be two people. Yeah, the details of the project will also be put on the Blackboard a little bit closer to it.
Two people also for the presentation?
The presentations can be bigger. Like 3 or 4 people is perfectly fine for the presentations. Okay, more questions? Okay, if there are no more questions, then we can move forward. So let's start by kind of looking at what AI is. What is it useful for? Yes?
Is it recorded or?
Yes, I think it is recorded. At least I'm hoping it's recording. So artificial intelligence is today basically used in almost everywhere, right? I will not kind of give an exhaustive list of all the places. We would be here forever. Just to give you a couple of ideas, like in the area of transportation, there is a lot of different communicating pieces and a lot of different AI being used, and of course, even more AI coming ahead. We are starting to see different kinds of robots in the homes, in the industry, things that look like, okay, can we actually have pets and so on. I'm sure almost everybody has robotic vacuum cleaners, so that's kind of well-known stuff by now. They do use various kinds of AI, of course. But you kind of look a little bit back and see where things started. Like one potential way of looking at it would be a simple game like this, where the computer played against a human. And so you can think of a game of Pong, and you could adjust the difficulties of how well the computer would play, but you could have, well, back in those times that counted as fun. Compared to today's games, maybe it's not. But there are more obvious cases of use of AI in games. And I guess many of you have heard about the IBM Deep Blue. So this is the machine which actually beat chess grandmasters. So the time when we actually noticed that computers are better at chess than humans. So it's a it was pretty big machine by those time standards. Today, the performance is not very impressive anymore. But I mean, you can think about the way it was working. It calculates a lot of different possible moves. So it looks ahead with kind of brute force algorithm where it tries to evaluate a lot of different moves and picks the best one. So in 1997, Deep Blue beat Garry Kasparov for the kind of title of the master in chess. Now, the way this computer plays is of course very different from how humans play, but it actually does it pretty well. Now, one interesting aspect is that in 1957, when basically the term of artificial intelligence was coined, this is the first time people started talking about artificial intelligence. And then those researchers predicted that it will probably take them roughly 10 years to beat human grandmasters in chess. They underestimated this a little bit. It was slightly more than 10 years. And you can kind of guess, predicting the future is difficult. Of course, chess is not the only game. Another kind of game is TD Gammon. So the algorithm playing game is TD Gammon. So it plays this kind of a game. And the reason I'm mentioning is because it's a different approach towards game playing than what Deep Blue does. Deep Blue was heavily programmed with existing human knowledge about how to play chess. On the other hand, the TD Gammon is actually trained by self-play. So it plays against itself and learns from when it wins, when it loses, about what does it make, what makes a good or bad move. So instead of based on search, on trying to look at all the possible moves and evaluate them, it does some kind of pattern recognition where it identifies types of moves which are good. And this is important because some years later, it led to another big thing. You also might have heard about the AlphaGo, where in 2016, computers have also beaten humans in the game of Go. So not just chess, but also Go. And I don't know how much you know about the games. After Kasparov lost, basically many people agreed that Go is the next big step because it's a very different game than chess. And the same technique of brute search that worked for chess wouldn't work here. So you need to use something else, something smarter in order to beat humans. And this idea of basing the computer on learning, on playing against each other, discovering patterns in moves which lead to winning versus losing, is also used here and worked very well. So that was another recent big success of AI. And that has also later led to what is called AlphaZero. And the difference is that the original AlphaGo algorithm also used a lot of human knowledge in terms of how to play the game. But after that, because it extended this knowledge with learning, there was also a version where zero stands for zero knowledge, meaning it learned from scratch. It didn't use any pre-existing notions about how to play the game from human experts. It started from scratch and learned everything by self-play, by playing against each other. And as you can see, training, it took time. It's training in days, but it actually reached higher levels after roughly 1 day. And in the end, it was able to improve farther than the version which used human knowledge. So it actually turns out that when you take all of the human knowledge, everything that people have learned about playing Go over thousands of years, it hurts the machine. In just like a month, you can learn more than we have learned over the ages, which is a little bit humbling if you think about it. But it's of course also related to the fact that those computers still think very differently than we do. But there are some, at least, ideas about, okay, where we are going in the future in terms of the kind of impact of AI. Now, the big question is why are we talking about games? Like why are we wasting our time on something that mostly children do? Of course, not just children. I mean, the grandmasters in chess or in Go, they are professionals. But what's the point? And the real reason why a lot of AI research starts from games is because you have this safe and objective environment. You cannot hurt anybody, so you can basically do whatever experiments you want. If you try to show that AI works in, let's say, autonomous driving or in medical field, you need to add a lot of checks and regulations just to make sure that you don't harm anybody. Games are safe. You can play, you can try whatever you want. There are no regulatory bodies which make things slow and so on. And the other big part is this objectivity. You have clear set of rules and you have clear goal. So you always know that if you win or you lose. If you are doing autonomous driving or healthcare or anything else in the real world, things very quickly become fuzzy. It very quickly becomes questionable if you actually made the right decision or not. How do you evaluate it? You have different trade-offs to look at. You don't have to worry about those things in games. You know if you are making an improvement with no biases into it and so on. So the point is to simplify the complexity of the world so that we can actually try to build better algorithms. And then those algorithms will be used in more realistic fields once they are actually sufficiently mature. So we may also hear about this distinction between narrow AI and general AI. So narrow AI is AI designed specifically for a given task. For example, Deep Blue or AlphaGo, they can play chess and Go, but they cannot do anything else. They cannot even play the opposite game. Like if you tell AlphaGo to play chess, it will fail miserably. If you tell Deep Blue to play Go, it will fail miserably. They are narrow. They are only done for specific tasks. Now, ultimately, you would want to develop some kind of general AI, which can do things that humans can, solve many different tasks. But we are actually pretty far from that. But if you take this narrow AI and you try to use it, there is a lot of practical usefulness. I mean, some of you might have used this web page called Google. It uses a lot of AI to actually give you good results, right? Another different page from Google uses a lot of AI to do translations. Here's an example of a work in robotics which is using AI. And this one is surprisingly a little bit less, it is a little bit less impressive if you think about it. Let me just play you the video.
His assistant Stephen Miller are building a robot for the home that will fold our laundry.
We decided we'd tackle one particular clothing article, namely towels. So it's a rectangle, so it has a simpler shape than most other clothing articles. But it's that going from a towel just crumpled on the table to having it held up by two corners, that's really hard.
The robot sees the object through a technique known as background subtraction. His assistant Stephen.
We don't need to watch the full video. That wasn't very impressive. Like folding towers doesn't sound as difficult as playing chess or Go. Turns out it's a lot more difficult, at least for computers. There is work on using AI for the Mars Autonomy project. So a lot of different cars we have sent to Mars, driving there, collecting stuff. Building robots that navigate underwater, navigate in the forest. And of course, that brings us more or less to autonomous driving, which is all of hype today, right? So if you look at the history of autonomous driving, it basically started with DARPA Grand Challenge in 2005. The goal was to do autonomous driving 350 kilometers in the desert. So environment like this or this took about 7 hours, average speed 50 kilometers per hour. So Stanford group led by Professor Tran won, and the second team was CMU, which was 10 minutes slower. They must be really pissed. It took 7 hours. They lost by 10 minutes. Especially if you think this was the second edition of the challenge. The first one was in 2004. And back then, the best car barely went more than 10 kilometers before crashing. So just think about the progress that happened in 1 year from here to there. And then you lose by 10 minutes. I don't know how they survived that. So turned out, autonomous driving is not that difficult. You can solve it in 1 year. And then next year, there was the urban challenge. So the idea of doing the same thing in a city. Obviously, driving in a city is easier than driving on a desert. But it turns out it's not, it's harder. So since then, we are basically still trying to solve the self-driving challenge. And there is a lot of progress in that area. There is a lot of companies which claim success. Big challenge here is how to make it realistic. And this is an early example of a Google self-driving car, which basically has like $150,000 worth of equipment. With that kind of equipment, it's not a very difficult problem, but you cannot really have like a LiDAR sensor, the big thing up there, which scans the environment, which is worth more than like 2 or 3 normal cars. That's doable, but that's not really the point. So the question then becomes, how do you make self-driving cars affordable and feasible? And here is an example from Volvo Cars, who had a Drive Me project, which was described as in 2018, 100 customers will drive XC90s on the streets of Gothenburg.
In 2017, Volvo Cars will put 100 self-driving cars on the streets of Gothenburg in Sweden, with real customers in the driver's seat. The unique Drive Me project is a part of Volvo Cars' journey towards a crash-free future. Volvo has now designed a complete system solution. Multiple radars, cameras, a laser, and ultrasonic sensors monitor the complete 360 view of the surroundings. A network of computers processes the information, high-performance GPS, and a cloud-based 3D digital map, continuously updated with real-time changes in the traffic environment. If anything fails, there is a backup solution, just like in an aeroplane. This includes vital components such as computers, sensors, steering, and brakes. On the road, the car is able to handle even the most complicated scenarios. The technology is so reliable that the driver can focus on something else without having to pay attention to the traffic. Just like good drivers, potentially critical situations are approached with sensible caution. And in an emergency, the car reacts faster than most humans. When autonomous driving is no longer available due to exceptional weather situations, technical malfunction, or reaching the end of the route, the driver is prompted to take over again. If the driver doesn't take over in time, the car will bring itself to a safe stop. With the Drive Me project, Volvo enters uncharted territory in the field of self-driving cars. Taking the final step to driving safely in real traffic with ordinary people behind the wheel has never been done before. And for drivers, the everyday commute transforms from lost time to quality time, open for work or pleasure. The choice is entirely yours.
That's nice.
Yeah, but you won't need license anymore. Driving license with.
Well, that's the idea. At some point, maybe you will not. They didn't actually succeed with that. Right? There is no 100 Volvos driving on the roads of Gothenburg autonomously and so on. As with many things, turned out to be a little bit more difficult than they expected. So that there is still a lot of challenges and active research in those areas. One thing I wanted to mention is that there is Grand Cooperative Driving Challenge. So basically adding communication to those vehicles. So in 2011, there was a competition of 11 teams and we took second place. In 2016, we won.
Yeah, finally, very tired, very short night, but I'm very ready.
Okay, a little bit nervous. We have tested everything on a different place, so anything can happen.
Then the platoon can start for the first heat.
All vehicles merged automatically. Afterwards we will switch to the emergency scenario. And then finally the crossing.
Perfect.
It's amazing to be working with all these people.
So the winner of the GDC 2016 is the team from Media, so Hansard.
So that was mostly a team of our engineering students. And of course, if we start thinking about why are those things happening now, that there is a number of reasons, not the least of those is the increase in power of computers. And you actually need sufficient computational power in order to be able to do those things. Memory becomes cheaper, computational power becomes cheaper, it's easier to do sufficiently complex calculations, so you actually can benefit from the AI. And you cannot fake intelligence with too little computational power. But there is also a change in kind of paradigm of how we think about intelligence itself or science. Like if you think back in time, roughly until 17th century, science was purely empirical. Science was observing the world and basically describing what you see. Then we started with theoretical science, where we gave models. We had the laws of motion, for example, and we were trying to do experiments to validate those models. So you would generalize the understanding, you would build better models. And then roughly in the 1950s, we started with computational science. So the use of computers actually changed almost all the different branches of science. Obviously we have computational biology and so on. but we have computational linguistics. Every single field of science, you have the computational version of it, because we have models so complicated that we cannot handle them otherwise. And we are now starting with what some people call data-based science. So where you go kind of one step farther, because you have such a flood of data from instruments and so on, that you actually need to automatically pose new hypotheses and so on, which is an important part of kind of rethinking the idea of science. So if we take a step back and try to think about, okay, what actually is artificial intelligence, there is a number of different definitions which kind of try to capture all of those things, right? You can talk about enable computer systems to perform activities that are considered intelligent, making intelligent machines, design and study of computer programs that behave intelligently, concerned with intelligent behavior in artifacts, rational agents in environments. So there is a lot of different ways in which you can look at the AI. That actually might be a good place for a break. So let's have 10 minutes break, and then we will continue. So let's keep thinking about what is AI again. A lot of different definitions. The exact wording is not that important, but you can think of it in kind of 4 different broad categories. So one thing is, if you go back like 1978, the automation of activities that we associate with human thinking. That's one possible definition. And then a slightly different definition is the study of mental faculties through the use of computational models. Yet another is art of creating machines that perform functions that require intelligence, or branch of computer science that is concerned with automation of intelligent behavior. And if you think about those 4 example definitions, you can see the first one talks about thinking like a human. It's very much focused on, okay, how is the thinking done? And it should be similar to how humans think. While the next one is about thinking rationally. So basically making good decisions. Doesn't matter if it's exactly the same way as humans do it, but as long as you make good decisions, you are fine. And then the next one is about acting like a human. So it doesn't really matter in what way you do the thinking. The question is, do you kind of demonstrate or exhibit the same intelligent behavior? And then yet another is acting rationally. And again, this distinction between human and smart in a sense. You might be doing things very different from humans, but as long as those are smart decisions, you are fine. So looking at those definitions, there are different aspects that you could study in terms of artificial intelligence. There are people who are looking at artificial intelligence as a way of understanding human psychology. That's perfectly fine, but that's not really what we will do in this course. In this course, we will mostly focus on this aspect of acting rationally. So we are talking about how to make machines which solve the task in the best possible way. Doesn't matter how similar they are to what humans do. And again, historically, this distinction wasn't really clear. I mean, you might have heard about the Turing test. That was one of the first definitions of, okay, what AI could mean. How do you test for artificial intelligence? Well, so Turing had this idea. If you put a human in front of a terminal, and there are 2 rooms, in one, there is another human in front of a terminal. In another, there is a computer. Of course, back then, Turing couldn't imagine that you could actually talk to a computer. Right now, you could, like it makes no big difference if the interface is voice or typed. For him, it was inconceivable that you could actually talk. But the idea still being, if this guy cannot distinguish if he's talking to a real human or to a machine, that means the machine is intelligent. But this kind of definition focuses a lot on this similarity to humans, not so much. Like, if the computer is super intelligent, actually smarter than a human, it would fail the Turing test, even though it clearly, by definition, has a lot of intelligence. I don't know how many of you have seen this movie. It's actually quite nice. We will not see the whole movie here, just the trailer.
Over the next few days, you're going to be the human component in the Turing test.
One day the AIs are going to look back on us the same way we look at fossils.
Hello.
How do you feel about her?
Oh man, she's amazing.
You're impressed?
Yes.
Do you want to be my friend?
Of course. Now the question is, how does she feel about you?
Do you think about me when we aren't together?
Did you give her sexuality as a diversion tactic?
This is your insecurity talking. This is not your intellect.
Did you know that I was brought here to test you?
Does Ava actually like you? Or is she pretending to like you?
Nathan, he isn't your friend. I'm wrong.
Wrong about what?
Everything. Do you want to be with me?
Can we talk about the lies you've been spinning me?
What lies? What lies?
You have to help me. You have to help me. What will happen to me if I fail your test?
It's actually quite interesting and somewhat realistic. Of course, this is science fiction, right? That's not where we are. This is where we are.
We're going to treat you to a short round of Jeopardy. It's going to be hosted by a member of our Jeopardy Clue Crew. Please welcome Jimmy McGuire. Gentlemen.
Good morning, everybody. Thank you for being here. What do you say we play Jeopardy? Let's get right into the Jeopardy round. These categories: a man, a plane, a canal, Erie, Chicks Dig Me, children's book titles, My Michelle, MC5, and finally, vocabulary. Ken, you're in the first position. Please make a selection.
I've never said this on TV. Chicks Dig Me for 200, please, Jimmy.
Kathleen Kenyon's excavation of this city, mentioned in Joshua, showed the walls had been repaired 17 times. Watson.
What is Jericho?
Correct.
400, same category.
This mystery author and her archaeologist hubby dug in hopes of finding the lost Syrian city of Urkesh. Watson.
Who is Agatha Christie?
Correct.
Same category, 600.
At the Olduvai Gorge in 1959, she and hubby Lewis found a 1.75 million year old Australopithecus Boise-eyed skull. Watson.
Who is Mary Leakey?
You're right.
800, same category.
Harriet Boyd Hawes was the first woman to discover and excavate a Minoan settlement on this island. Watson.
What is Crete?
Yes.
Let's finish Chicks Dig Me.
At Mount Carmel in Israel, Dorothy Garrod was the first to find this prehistoric human skeleton outside of Europe. Ken.
What is Neanderthal?
You're right.
Let's go to children's book titles for 200.
Marjorie Williams' story of a stuffed toy that comes to life, the blank rabbit. Brad.
What is Velveteen?
You're right.
MC5 for 200, please.
He's worth every penny as Alfred Pennyworth in The Dark Knight. Brad again.
Who is Michael Caine?
You're right.
MC5 for, let's jump down to 800, please.
Edgar Degas' style influenced that of this female American impressionist. Brad.
Who is Mary Cassatt?
Correct.
And MC5 for 1,000.
The film Gigi gave him his signature song, Thank heaven for little girls. Watson.
Who is Maurice Chevalier?
Correct.
Same category, 400.
The parents of this 52nd governor of New York immigrated to the United States from Salerno, Italy. Watson.
Who is Mario Cuomo?
Correct.
Let's finish MC5.
This
can stop here. Spoiler alert, he crushes them. Again, it's a game, right? Still smaller, simplified environment, but it's not chess anymore. This is much more realistic. So the question then is how those things happen. And one way of looking or kind of starting to look at it is with this notion of intelligent agents. So in order to talk about intelligence, you basically need to have this distinction between environment and the agent. An agent can be physical agent, like a robot here, can be virtual agent, completely in a computer, that doesn't really matter, but you need to have some kind of environment. And then you need to have some percepts and some actions. So you have some sensors that allow you to observe the environment, and then you have some effectors which allow you to do things in the environment. And then you can talk about making intelligent actions and so on. And intelligence is basically the thing that happens in the middle, right? How do you go from whatever you observe to figuring out what to do? And here it's very important, the notion of rational agent. You might have heard the notion of optimality, like doing the best that's possible. That's a little bit too strong idea, because you need to simplify it into rationality, where rational decision depends on the agent's percepts in the past. Optimal decision might require you to know the future, might require you to know things which you have no way of knowing. So you cannot rely on future observations to decide what to do in reality, of course. So the optimal decisions would be if you have rationality and omniscience, so if you know everything. If you don't know everything, you cannot always do optimal decisions. So then the rational is the best you can do given the knowledge you have. Right? And then you want to build agents which make as close to rational decisions as possible in as many situations as possible. That's basically the definition of intelligence that we will be using here, even in the complex environments, right? It's obviously really easy to do the best thing in a simple environment. Like if you play tic-tac-toe, it's easy to figure out what the best move is. If you play chess, it's harder, Go even harder, Jeopardy even harder, and so on. So if we take a very simple example, let's say we want to have a vacuum cleaning robot. Of course, it can be many different kinds. Let's start with an extremely simple robot where you have two rooms and there is some dirt in it. What we need to describe is we need to describe several parts in order to talk about this. So we need to have some kind of performance measure. We need to know what is our goal. In this case, to maximize the number of clean rooms, minimize the number of dirty rooms. That would be our performance measure. If we want to formally talk about intelligence and achieving goals, we need to know what we measure. And from engineering perspective, it needs to be clear, well formalized. And then we need to describe the environment. In what environment this robot operates, because depending, like an action which is good in one environment would not be good in another. Right? So we could say that we have discrete rooms. We just have two rooms, simplifying things. Each one is either dirty or clean. We don't talk about different degrees of dirtiness, just the binary dirty or clean, and so on. So a lot of different ways in which you can describe the environment. We can say there is just a single agent. There is only the robot and nothing else, and so on. And then we need to decide what are the actuators and sensors for the robot. So how the robot perceives the world and what kind of actions it can make. Once we have all of those things, we can try, or we can kind of program the robot, we can describe the algorithm, and then we can start talking about how intelligent it really is, how well it can respond to different situations, and so on. So in this context, it's important to kind of think about what are the different types of environments or different challenges So you can think of single or multi-agent environments. Is the agent you are describing the only active thing in the environment, or is there many agents? And maybe it needs to communicate with them. That requires more intelligence in a sense. It's a more complicated setting. Similarly, you can have static or dynamic environments. So does the environment change by itself, or is our vacuum cleaning robot the only thing which affects the environments? If you want to be making plans about the future, obviously you need to take into account possible dynamic environments. Discrete versus continuous, episodic versus sequential, a lot of different ways of kind of describing it. I will not go through all of them. I just wanted to mention the last two, basically the accessible versus inaccessible. So how much does the agent know about the environment? And the most typical case here is partially observable, which basically means that you can observe some things about the environment, but not everything. And that's the most challenging case, because if you imagine a robot which has no sensors, it's not difficult to program it in the best possible way. It cannot really react to anything. So it's not, there is not high requirement on the intelligence. And then if you observe everything, again, things are reasonably easy. It's really tricky if you observe some things, but not everything. And there is a similar challenge with deterministic or non-deterministic. Can you actually predict the results of actions perfectly or not? And in reality, a lot of the things we do are non-deterministic. So if you think about the different types of agents, how can you actually be making those decisions? The simplest one is what is called the reflex agent, which is an agent which only makes decisions based on current observations. It has no memory, it has no planning capability, it just observes things and does stuff depending on what it observes. Right? So it cannot really solve a lot of complex problems, but sometimes it can work quite well. So in this simple case, of course, it sees an apple and tries to reach it by jumping. And then you can have a smarter robot, which actually does some kind of reasoning, which is inferring new facts from what you already know. Right? So imagine that the robot actually knows how far it can jump, so it can try to calculate the trajectory, and it will actually notice, okay, it will not reach the apple, it's not strong enough to jump there, and so on. And that's kind of what we typically associate with intelligence, right? You need to have this capability in order to be considered intelligent. That's what people do. People and computers do it in different ways, but the basic idea is kind of the same. And when you try to compare computers, AI with humans, and the question whether computers can think or not, I like this quote. They do the same thing we do as when we think, but they do it differently. So the question is, does it make sense to ask this question? And then kind of the next step is planning, where you not only can actually reason about consequences of your actions, but you can consider multiple alternative scenarios and alternative sequences of actions. Right? So now you have the robot who can actually move away from the apple, get a tool, and come back, which sounds like a bad idea because you want to get to the apple. Why would you move away, go somewhere? But if you have a plan, if you know why you are doing it, that might be the right action. So this idea of building sequences of actions is important. And the challenge is that this becomes very, very complex. Like if you think about all the possible actions you can do and then sequences, it's a huge number of things to consider. So we need clever ways of kind of simplifying it for the agent to do the planning in reasonable time. Now, in this course, we will mostly be talking about techniques related to what is called machine learning. And it's not exactly like in this picture, but conceptually, it kind of is. Right? So The alternative to machine learning is what is called deductive reasoning. So deduction is a normal, I'm sure you understand what that means. So basically when you have initial knowledge and you reason about, okay, what are the consequences of what I know, and you come up with new information. But in many cases, you don't have this initial knowledge. So then you need to do the alternative thing, which is called inductive reasoning. So induction is based on the idea of concept generalization. So you make observations and you generalize based on that. You have observed the sun rising on the east throughout all of your life, and you make a kind of leap of faith that it will keep doing that forever. It could start rising on the west tomorrow. We have no actual way of knowing it will not, but everything we have seen until now suggests that it will continue doing the same stuff. So induction and deduction are kind of two sides of the same thing, right? Because you go in induction, you go from observation or some kind of experiment, you generalize the results, and then you build a theory. And then this theory allows you to make predictions so that you will know, or you can deduce what will be the results of the experiment that you have. And those two things go hand in hand, because if you have the right, you can get the right theory from sufficiently many generalizations, and then this theory will make good predictions about the future, right? So it's kind of the same idea here. You go from theory to hypothesis to observation, and then you can confirm it with observation, or you can go from observation, discover a pattern, create a hypothesis, and then by confirming it, build a theory. That's how it works. And ultimately, the end goal of all of this is, again, the call here decision support. So using AI to make smarter decisions, right? You want AI systems to help you with making decisions. And that basically includes kind of moving from data, information, knowledge, wisdom, decisions. So we can talk about this kind of knowledge pyramid. And then if we think about what specifically is data mining, it's not really hitting data with big sticks. It's much more like this. The part about finding something is the heavy hitting into rocks, not really. So the data mining is kind of a combination of, we could call statistics, artificial intelligence, machine learning. There's a lot of different ways in which you can try to frame it. Basically, it's about discovery of patterns in data. So you have data, and then you want to find some kind of useful patterns in that data. And when you try to define what useful means, you can talk about like non-trivial, implicit, unexpected, previously unknown, a lot of different ways of phrasing the same thing. But the idea is kind of to do something, to find something new. And again, this comes back to the question, why are we so interested in data mining right now? And people have said, we are drowning in data, but starving for knowledge. Like we are collecting a lot of data, but it's actually difficult to get something useful out of it in many cases. And there is a lot of other words that you could potentially use. Like when people talk about knowledge discovery, data analytics, you could argue tiny bit differences between all of them, but the basic broad idea behind all of them is roughly the same. What is not the same is, for example, like search or query processing or expert systems. Those are different. Now, okay, the idea of data mining comes to a large degree from what is sometimes called this data gap. I'm sure you have heard of it, and it can mean a lot of different things. But one way of looking at it is we are actually having more and more data right now, but we need to make decisions faster and faster. So the gap between the time to decide and how much data you need to analyze in order to make decisions is growing if you compare now to like 10 or 20 years ago. Another way of looking at it is we are collecting a lot of data, but the amount of data we collect is growing much faster than the amount of relevant data we collect. because it's getting easier to collect the data, we are collecting a lot of useless data, or pretty much useless data. Like the harder it is to store information, the more selection you do before you actually store it. And now we do no selection. Like we basically store everything or almost everything. So it is getting harder and harder to find stuff there, which means we need those automatic tools in order to help. So the underlying key to data mining is always and always will be the data. So if you think about what makes the data so important, imagine that you are trying to build a system which identifies faulty medical devices. You have a factory, and sometimes the faulty device is produced. How do you find it out? You want to look at patterns in the data. So let's say that you get a lot of production data, different days of the week, times of the day, what machine was doing things, what operator, all of that. The question is, what happens if the true factors causing the defects are not in your data? Right? Let's say that the defects are caused by raising the temperature in the room. You don't collect this data. That means it's going to be basically impossible for the AI system to find those patterns. So the typical way of kind of doing AI is you want to start with all the data or as much data as you can, because then you can ensure that the real cause is there. And that's the reason why people have been collecting so much data and why when you start doing some kind of AI analysis, you want to start with as much data as possible. Because we have techniques for kind of pruning the useless data. But there is nothing we can do if the important data is not included. So then how do you make sure that you collect all of the important data? You can never really guarantee it, but there are different ways in which data is collected and they all matter. So you can have automatically generated data, for example, for different sensors or so on. And then the question becomes what sensors are available. Right? Do you have a temperature sensor? If you don't, you cannot have this kind of information. But even if you have the sensors, how do you transmit this information? In a modern car, you have thousands of sensors, but actually transmitting and storing this information would be expensive. So you don't want to do all of that. Then how do you store this data? Even though storage is cheaper, it's still not free. If you are trying to store huge amounts of data, it will be expensive. If you don't have the sensors that you need, maybe you need to install additional ones. And then the question becomes, okay, which ones, how, when, and so on. Sometimes you need to do special data collection experiments. Like you would want to collect data from normal operation, whatever it is that you are doing, but sometimes you can't. So you need to design new experiments specifically for collecting the data. And sometimes you need to get the data from the humans. So you need to have surveys or questionnaires and so on. And that also comes with its own challenges. So for example, there is a lot of talk now about gamification in different contexts because we need to collect more data from humans and humans don't like providing data. I don't know how happy you are answering surveys, but I don't know anybody who really likes it. So we need to find better ways of getting this. And then the other big question is, can you get labeled data or just unlabeled data? So can you actually, if you are collecting, let's say, images from a traffic camera, how do you know which situations on the road are accidents and which are not? Whatever label you are interested in, it's usually difficult to get it. We'll come back to some of those aspects at least. So if you think about how you can collect the data, there is not single best way of doing it. There is many different things, but what you need to consider is basically, what do you need to know? Like, can you get away, or do you want to get numbers or do you want to get stories? Okay. where this data currently is. Like, is it data about the environment? Like, if you want to have temperature data, you can just measure it. But if you want to get emotions or impressions data, you can only get it from humans. There is no way of measuring it directly. What are your resources? How much time you have available for this collection? How complex is the data? And so on. So a lot of different things that you actually need to consider. And then if you decide that you want to be collecting data, there are a couple of things that you should think about. At least consider multiple data collection methods, because that both increases your accuracy and gives you some kind of a safety net in case something doesn't work. And if you don't collect new data, but you use existing data, you need to know some basic information about it, like how it was collected, why, how it was processed, cleaned, how much data is missing, how was the accuracy of this data verified, and so on. Because it's very easy to find existing data which seems relevant for whatever you want to do. But if you don't actually verify that it will work, you might spend a lot of time analyzing it and then notice that it doesn't work because, for example, it doesn't actually measure what you need precisely enough, and so on. On the other hand, if you do collect original data, you need to account for how much burden it is. Because if you do a survey which takes half an hour to answer, nobody will answer it unless you provide very strong incentives for doing that. So that becomes very expensive. So you need to balance it properly, right? And then make sure that you test that your data collection works. It's very easy to have a data collection which only collects parts of the data, for example, and so on. Make sure that you have a clear protocol for how the data is collected so that you actually collect the data all the time in the same way. If you are measuring something, always measure at the same time in the same place and stuff like that, because otherwise your data might have some bias. You might have unrelated changes in your data, which will make the future analysis related. And make sure that you keep a record of what exactly you are measuring, how, verify the accuracy, and so on. So it sounds easy to collect data, but it's actually not. I will not go too deeply into it. But if you think of different ways of collecting data, you can talk about the structured approach, where you actually collect all the data in exactly the same way. So if you have a survey with just the checkboxes, that's a structured way. All the data will be collected in the same way. If you have free text entry, then it will be harder. When you then try to analyze this data, it doesn't have the same level of structure anymore. And this, to use some kind of structured approach is especially important if you do it for multiple sites or multiple clusters, or you want to compare different, let's say, interventions. Imagine that you have several people collecting the data. You need to make sure that they do it the same way, because if they do it differently, you might get different results. And then the alternative is to have a semi-structured approaches where you have the general purpose or general kind of procedure for getting the data, but the details are actually different every time. So it's more open and fluid. So if you have some kind of an interview in which you have follow-up questions, then every interview will look differently. So you'll get somewhat different information from every person. So you don't have this rigid script. And there are strengths and weaknesses of each of those approaches. So there's not like one is better than the other, but you need to understand why you are using it. And if you are thinking about, okay, so what do you actually want to measure? So what is a good quantity to measure? You basically need to answer 4 questions. Is it relevant, credible, valid, and reliable? So relevance means, does it actually measure what you are interested in? In many cases, you end up measuring whatever is easy to measure, and that might be somewhat related to what you are really interested in, but not exactly the same thing. And again, you need to be at least aware of that fact. Credibility is about, is it believable? Like, can you convince somebody that actually what you are measuring captures the information you are interested in? Validity is about how close your measure is to what you want to actually capture. And here is one example. Like, you can have access to like waiting lists, and you can say, well, waiting list is kind of estimation of a demand, but not really, right? It's a pretty weak estimation because it also takes supply into account. So this is one example of what you want to look at. And then we have reliability, which is basically the precision of the data. So how accurate your data is, right? If you want to measure speed by using a stopwatch, it all depends what speed you are measuring. If you measure speed of walking, probably works fine. If you want to measure speed of light, not so much. So the actual precision you need depends on what is it that you are measuring, and then you need to estimate, is my measurements actually going to be reliable? And then somewhat related to the structure and semi-structured approaches is also the qualitative versus quantitative approach. So qualitative data gives you descriptions, right? So it could be some kind of self-reported values, and they're not so structured. They're generally easier to get, and they can provide what's called rich data with a lot of details and so on. But it's typically challenging to analyze this data, challenging to draw conclusions. And the alternative here is to have quantitative approaches. And actually, we will mostly deal with this type of data in the course because this is typically what you will use machine learning on, mainly because it's much easier to collect large amounts of such data. So we assume here that the data is in some kind of numerical form, right? So that only applies to things which you can precisely measure. So it can be age, cost, length, but there is a limited number of things that you actually can measure this way. So typically, the quantitative approaches are harder to develop, but once you do it, the data is easier to analyze. And yet another dimension for collecting data is obtrusive versus unobtrusive methods. So basically, are you collecting data by directly interacting with the object you are measuring or not? So if you do things like interviews, surveys, focus groups, that's obtrusive methods. You are interacting with whoever you are observing. And if you do document analysis or Google Earth or observations from a distance, then you are not interacting. And the challenge with obtrusive methods is that you might actually influence what you are getting. Especially in, for example, healthcare domain, it's very well known that what is called white coat effect. If you observe people, if you talk to people, or even if you measure things at a healthcare center where there is a lot of doctors around, you will get different results than if you do it at patient's home, because we all react to the environments. And the obtrusive methods, by definition, they change the environment in which the observation takes place. So as an example, you can take a look at something like Google Earth. There's a lot of really interesting information you can collect there. So just think a little bit about what would be possible to get. So if I go a little bit more specifically into different ways of collecting information, so one would be participatory methods. So you basically involve groups or communities So you can have community meetings, mappings, and so on, and you collect information that way. So generally, this is one of the most accurate methods of doing things, but it's also quite expensive. Like it takes time to do this. The next type of method would be with observation. So you basically just observe what is happening without interactions. Right? So you don't ask for explanations, you don't collect anything more, you just observe what happens. And you can do basically anything in this way. You can observe traffic patterns or layout of city or whatever else. The next possible method is with records and secondary data. So you don't observe the reality, but you observe already existing descriptions of that reality. Right? So you can have file records, computer databases, a lot of different reports, things like that, typically some kind of documents. That can tell you a lot about how the real thing looks like, but it's generally not as good as the direct observations. And the next possibility is also to not do any of your own data collection, but to use existing data sets. Right? And this is very common, especially in something like machine learning, where you look at what data is currently available because it's the cheapest. Right? But then there are a lot of those potential issues about validity, reliability, accuracy. If the data was not actually collected for the purpose for which you are using it, you have no guarantee that it fulfills that purpose. Maybe it does, but maybe it doesn't. So you need to be extra careful. And then one more thing which is worth mentioning is what is called triangulation, which is basically how can you increase the accuracy of your data? And you can do it by combining different approaches. So you can do triangulation of methods. If you collect the same information using different methods, you can then aggregate it and get better results. Or if you collect the same information from different sources, you can get better results because what is missing in one source might be included in the other, or some kind of bias in one source might not be repeated in the other, and so on. Right? And you can do the same with evaluators. So for example, when you do, again, giving this example from medical domain, if you want to have ground truth of diagnosis or something like this, you might ask 3 different doctors to evaluate the same patient, just to have more reliable results. So all of those things are important. And that's kind of the step 1 or step 0 maybe of data mining to get the data. So what do we actually mean by data? Like when we talk about machine learning database and data mining, what we typically talk in terms of data is we have some kind of a set of entities. Could be objects, organizations, people, whatever they are. And we'll often call them instances, samples, or examples. All of those things mean the same. And then each such instance is described by a number of attributes. So they capture the relevant properties of that entity. So if we are talking about people, it could be age, gender, hair color, body temperature, basically infinitely many possibilities, but different ways of describing that particular instance. And we often have different types of those attributes. So for example, you can have categorical attributes, like occupation being, let's say, teacher, or you can have numerical, like temperature or price. And the key difference is that numerical values you can compare. Right? You know that the temperature of 19 degrees is smaller than 21. But 19 and 21 are relatively close, and 2000 is much, much bigger. So you can do different kinds of comparisons. While for categorical variables, you cannot. You basically can only say it's the same or not. And if you have colors red, green, and blue, you cannot really say which one is bigger, which one is smaller. You know they are different, but that's more or less it. So what you would typically do is you have this kind of tabular data representation, where you have many different instances, and each of those is described by a number of attributes. So in here, you have sales. So each row is one sale or one order of whatever. And then each of those orders is described by a number of features or attributes. And that's the type of data on which we will be mostly working here and trying to figure out stuff. So let's say that you want to, for those orders, you want to figure out, okay, will the customer actually pay for it or not, right? That would be a classification task. You could use machine learning to try to figure out, okay, which of those will be paid and which of those will not be paid. But of course, that's not all. Like, there are other types of data as well. So the most obvious examples would be images, for example. They don't have this tabular structure. But you also can have time series. So if you have, I don't know, stock market, you would have price over time. And that's a different structure that you would want to look at. We will touch on this a little bit in the course, but actually very, very little. So you can mostly focus on the tabular data. And then looking at the kind of the data mining process, you can think of the 4 stages here, where we start with some kind of data sources, which we talked about a lot. And then you have some exploration where you try to understand this data. You build some kind of a model, could be neural network or whatever else. And then you deploy this model and actually use it in the future for those things. And you can think of it also in terms of this information hierarchy or knowledge pyramid, where you kind of go from data to information to knowledge to wisdom, where kind of each of those is richer than the previous. So coming back to this question of what is data mining, now we can be a little bit more formal. So it's an algorithmic process. So you have something that you can feed into a computer, where your data is input and useful patterns are the output. And when you think about what are useful patterns, it can be a lot of different things. You can have like a description, abstraction, or summary of data. You might feed a book and want to get a summary of that book. You can have classification or association rules. You might want to say, okay, how do I know, is this patient sick or healthy? You might want to find two clusters, regularities, outliers, or deviations. You might want to look at the, I don't know, credit card history and see, are there any fraudulent transactions there? All of those would count as useful patterns. So there is a lot of different types of data mining that you could investigate based on all of those things. And we will go through that briefly. But the key concept here is this idea of discovering something new. Right? You are looking for something which is not obvious from the data. So if you look at this data mining process, you would typically do data cleaning, integration, selection, modeling, evaluation, and knowledge. We will cover those things in more details on the future lectures, so I will not go deeply into it. But I just wanted to highlight that this is actually kind of iterative process. You will come back to those ideas over and over again. But it's also important to understand that data mining doesn't really have wisdom. So it will find those patterns, but it will not actually tell you what to do with them. Like once you discover the pattern, it's still up to you to decide what to do, how to act based on that pattern. So you might will get help with planning strategies for a company, but you will not get a strategy directly out of that. And also, majority or all the methods we will talk about at least are based on statistical analysis. So you are looking for statistically significant patterns in the data, which means that you are actually looking at the multidimensional data, some noise models, and trying to find mathematical properties that fit. So you optimize the expected value for some performance over unseen data. you are not interested in knowing how well your method works for the data you have already seen. You are interested in how will it perform, or making a guess how it will perform in the future. That's your goal. Right? And then we have two main ways of doing machine learning. One is called unsupervised, in which you would have typically clustering, so grouping objects. And the challenge is that clustering is inherently subjective. So there is not single one best way of grouping objects. You can group based on different criteria. And you can have anomaly detection where you try to find strange things. And strange things also can mean many different things. This value is obviously strange, it doesn't fit the rest. But this flat thing here is also strange. How do you discover all of those? And then the other big branch is what is called supervised machine learning, which is finding patterns which are associated with some labels. So one typical example is the iris dataset, where you have 3 different species of iris flower, which are described by petal length and petal width, and you want to figure out what patterns correspond to each species. So there, what you need is a representative training set. So you need data on which you train. So you might teach the machine, for example, in distinguishing what is important and unimportant email, and the machine can then do it in the future. But of course, you need the data set to be representative. Right? If your data is very different, then it doesn't work. And then it's also important to understand that machine learning is a 2-step process. You start by creating some kind of a model. I'm running out of time, so I will not go through the details. And after you build it, then you can use it in the future, right? So you train your model and then you use it in the future. I will skip those 2 slides, but then the other important part is, as I said, all the machine learning is based on statistics, which basically means you discover patterns which are common in some given population, but they don't actually tell you anything about any specific individual in this population, other than typical members of this population have this behavior, which is very, very important when you start talking about fairness and so on. There's a lot of discussions now about AI and using it in kind of sensitive areas and how that works. So that's something to think about. I don't have time to talk about IID data, but you can look at those slides because they are interesting, I think. And then I also don't really have time to talk about the difference between correlation and causation, but I think you can also catch up on that. So thank you for today. Any questions? Okay, no questions? Okay, then thank you very much.